Okay, so I wanted to talk today about Corvus, which is a workflow tool for X-ray and related spectroscopies, first developed by Shauna Story, who was in our group, and now we're working on it with collaborators Das Pemerju and also with Fernando Vila and John Rare. So the motivation behind this is that, you know, many times when you're calculating things like EXAFS or XANES, but also lots of other spectroscopies, to get really good results, you need to use more than one complex scientific code. Sometimes these are fairly simple kind of workflows that you might use, such as structure optimization and then a calculation of RXES or XAS. And in other cases, it might be more complicated. So another example here is, you know, calculating using beta saltpeter equation, which is a fairly advanced kind of calculation to get dielectric properties or the loss function, and then have that as input to FEFF for using the many-pole self-energy, and then getting XAS out of that. Some other examples here are treating disorder, where you can calculate phonon properties, such as Debye-Waller factors, and use those as input to FEFF, or dynamic disorder using DFT and MD. What's been done in the past a lot is when you have some desire to use multiple scientific codes to get some improved simulation, the solution has been to build a new workflow to accommodate those calculations or automate those calculations, at least partially. And the result is that we accumulate, you know, a huge number of tools which have very similar structures, but might be written not in scripting languages that aren't portable, or and they're all written in different coding languages generally. And then they also have maybe multiple inputs, and the input structure is different and output structure is different. So it's not easy to exchange data between these different workflows, and you're kind of doing the same thing over and over. So we don't really want that. And instead, what we'd like to do is create a single workflow management environment, and then collect codes and interfacing tools in one place. And then that will be easy to use for general users. We'll include a GUI, for example, and then also customizable for advanced users. And finally, it should be portable. So we've chosen to use Python for that aim. So this code should be able to run on any platform pretty much. So let's just look at a simple example of Phonon Properties. In terms of how a workflow runs, this is very simple. You run one code and then you run another code is the idea, at least. So all we have to do is do some DFT calculation that gives you the dynamical matrix. Many DFT codes do this. ABINIT, Quantum Espresso, VASP, lots of different things do this. And then, you know, you calculate some vibrational density of states, pass that, or a dynamical matrix, pass that to our DMDW code that will calculate both things like Debye-Waller factors or phonon spectral functions, and that's all you need to do. That might be passed to FEFF in the end, but in reality, it's really much less simple than that. It's not that simple. And this kind of shows the problem here. A standard phonon workflow using ABINIT and DMDW has 4 different inputs files, right? And they all have different formats and things like that. And then, you know, each one is passed to a different code, which creates some output. and then that output has to be translated, sometimes manually moved between different directories and things like that. And then in the final analysis, you get your vibrational spectrum or your vibrational property. But this kind of multiple input format workflow, and where things aren't fully automated, is a pretty big barrier to users. Not that people can't figure out how to do it, but they may not really have time to deal with this, and it would be much easier if they could kind of learn one format for input output and not have to deal with all this translation. So this is where Corvus comes in. First of all, it's an automated workflow. This is a general sort of top level control diagram of Corvus. The user would choose a property and give some input, of course. You have to have some input for the system. For example, you choose a property that you'd like as your target property. That's what you want the workflow to calculate. It's going to read the input and populate this system properties data structure. And this data structure is what communicates with all the different pieces of the code. The workflow builder generates a workflow automatically. And then you have something to execute it and write output, and you finally end up with a target property. And the idea is that this thing communicates with all the external coding and handles all of the translation and input and output, so that you really only have to learn one type of input and output. In addition, it also has a very nice separation of general and code-specific tasks, so that the idea being there that you have exchanges which are independent steps of the workflow in the simple case, and they exchange data, general data, with the system dictionary, right? And then handlers are specific to each code, and they perform things like translation of output and input, and then also some other things like maybe some defaults for the particular property that you're looking for, and things like that. So the other thing that's nice here is that this is a property-driven workflow generation. So in the ideal case, again, you wouldn't really have to specify, although you'd be able to. You wouldn't have to specify exactly how the workflow goes. You specify a property, in this example, Debye-Waller factors, and it creates a dependency tree. And each of the nodes of the dependency tree could come from user input or a previous calculation. And so it's going to look for, so for example, here you have Debye-Waller factors. It populates this dependency tree. Some of these things were input by the user, the yellow ones. The blue ones are things that it did not find in the input. And so it's going to figure out what external codes can calculate that, and then it will start calculating or start creating the workflow that way. So here's just an example. I'm going to give a few different examples here. This is the kind of simplest example where you just want to do an optimized structure and then pass it to FEFF to get some kind of spectrum. In this case, it calculates XES and RXES. And the idea, again, is that you have an exchange. You have input by the user, structure, edge, absorber, for example, and then this is going to pass to the FEFF9 handler. In this case, there was actually, we wanted to calculate everything once before and then run the structure, optimized structure, and then calculate with FEFF again to see the difference as well. So it calculates, or it passes this to the FEFF9 handler, And then you have another exchange which gives structure to ORCA, and then this produces an optimized structure, and then updates the system database, and again passes this information to the FEFF handler, which produces input for FEFF9, and finally you get XES and RXES of this optimized structure. But one of the big benefits, again, is this minimal input that you have. So a lot of this stuff is smart default or automation. So in this case, you have very small amount of input. It's just the cluster. You don't have to define all of FEFF's potentials, for example, and then you also don't have to define many things in ORCA that you would normally have to define. You will have control over these, as you must, just in case you want to change things. But in this case, it's very simple. And this is kind of how it looks. At this point, we've changed a little bit how you run it. Everything's in an input file rather than, and you just specify the input file. But in this case, the workflow was sort of specified on the fly here, command line. And so you get a little bit of output here. And in this case, again, we had a molecule where we had a very similar structure molecule with which we started the structure at something with a very similar structure, but not exactly the same. I think we had N2 instead of N3 here. And so the structure was a little bit different, but you can see in the end with the XES, you get a pretty large improvement in the spectrum when you optimize this, and this is the kind of output that you would get. Okay, so let's look at another example. This is NWCHEM, where you do molecular dynamics and then you average over XES, and again you have exchanging of data, an NWCHEM handler that's specifically for molecular dynamics, or at least a piece of the handler that's for molecular dynamics. And then you have another piece that loops over the spectrum, or over the XYZ trajectory that's produced by the MD, and then calculates spectra and averages. And again, very minimal input, and you end up with a vibrationally averaged spectrum. And this was just a small, simple example that we did, but you can see that this vibrational averaging, in many cases, this can be important, of course. Okay, so another one that's very important for XAS, for example, is the Debye-Waller factor workflow. In this case, you're calculating a dynamical matrix using DFT, and specifically ABINIT, although we have handlers for quite a few other things as well. Excuse me one moment. I think my headphones are dying, so I'm going to plug them in. Can everybody still hear me?
Yes.
Sorry. All right. Can you still hear me, everybody?
Still got you?
Yes.
Okay,
Yep.
Great. Thank you. All right. So again, in this case, you end up with a fairly simple input and output. And you can apply this directly to XAFS, or you can calculate the Debye-Waller factors and look at those as output, for example. In this case, there was some simpler case, for example, GA gallium arsenide, and then also we did this with a bunch of diatomic and triatomic or small molecules, and just showed that the error compared to experimental data was quite reasonable for almost everything here. So this is, really nice calculation to be able to do, and we hope that that this will facilitate that. This is our Corvus workflow machinery. So some new functionality has also been added. And in particular, we have recursive functionality now. So this is going to allow us to deal with much more complex routines by treating workflows as external codes, in quote. So in particular, things like fitting, self-consistency, time evolution, convergence, things where you have loops over different pieces of the workflow, and you have dependence between different pieces of the workflow. So just to look at one example that we've already implemented, at least in some fashion, is fitting using LMFIT, which Matt Newtville is involved with. And so the idea is that it views LMFIT as an external code, even though it's not really, it's Python, so it's within the Python that it's calling this, but it passes other workflows to LMFIT as fit functions. So just to see an example of this input, you would set a target property which you would state as a fit, right? And then you give the fit its own target property, which it's gonna fit the XANES, and in this case it's using FEFF. And then you let LMFIT know where the experimental data is and define some fit parameters here. This is pretty minimal. This is just for GeCl4. I'm just kind of starting with some small molecules. And then, up here in the future, we'll have, instead of using a property called FEFF XESIRIXS, it will just be XANES. And then you can decide, or you can let the workflow machinery decide on which handler it should use to calculate the XANES. So for a small molecule, it might be better to use something else, either ORCA or Debye or some other calculation that has FDM and NES, say that has full potentials. In any case, you can choose lots of different properties here, or you will be able to, and then those properties should be general rather than specific to FEFF. So then the only thing down here that's missing is the cluster itself, the definition of the cluster. So, oops, am I missing something? Oh, I was just gonna kind of show how this works. That's right. So, I have a Ubuntu here, but I just thought how you would run it. You just give it an input file, and in the future, of course, we will have a GUI. We have the starting of a GUI already, but we're developing that. So hit run there, and it starts to run FEFF. It would run for probably quite a while here because it's doing a fit, but then you might take a look at exactly what things look like. Right now, it's just going to show the very first iteration, but in particular, you see a fit there, and at the end, it will give you all the parameters as output, of course. So I think this will be pretty powerful and useful. back to the slideshow. Okay. There we go. All right. Okay, so of course we'll have some other developments and things we are working on as well. We're going to be looking at putting in GW plus spectra, for example. We also have a start on using the cumulant to get X-ray photoemission spectroscopy. This is the real-time siesta version of this cumulant spectral function. And then that also can be used as a convolution to get improved X-ray absorption spectroscopy, which includes satellites. And then, of course, data analysis, which I just showed. Other things that, you know, are not so related to scientific software, for example, are things like database query, where you might, instead of calculating a property, you might look in different databases to get whatever property it is. And those could be experimental databases, or it could be things like the materials project, which have various properties. So
Josh, is this a good time to pause for questions?
Yeah, that would be fine. Actually, I'm almost done. I can answer these questions though now too. That's good.
Yeah. So we have a few questions. Young Ha, do you want to ask your question about ORCA?
Okay. The general question. I saw your input is relatively simple. You even didn't specify the charge and spin. So how does the software figure it out?
So the charge was actually specified in there. Let's go back up. Yeah, so it has a charge of 1, and it shows, you know, I think it's going to have a default spin, and rather than having something that you know, it's not necessarily going to figure out which spin you want. So if you want a different spin, then you're going to have to put that in, of course. And in some cases, it might matter more than others, and you have to be careful to make sure you put that in. So okay. This is minimal, I think, because of the fact that the spin didn't matter so much for this particular property.
Okay, another question I may have is, it looks like you have to pre-install a lot of package into your computer, or do you just put them as a bundle and we can just download and just install it?
I think so. What we're going to have is at least a software database. I don't know that we can really have it at everything as a bundle, obviously, because we have things like VASP in there as handlers.
Oh.
So not everybody's going to have access to everything. And in particular, a lot of the codes don't run on Windows, but we want all of these workflows. You know, there are a lot of simple workflows that people would really benefit from, just like configurational averaging, or, you know, simulating doping, where you don't necessarily have to do something super complicated if you're just doing replacement doping. And those would really benefit people, but we want people to be able to use those on Windows with FEFF, for example. So the way Corvus works is that you don't have to have any of these external codes, or at least you don't have to have all of them, right? So if you just have FEFF, you'll still have access to a lot of workflows.
Okay, cool. Thanks.
You're welcome.
And so Matthew, did you have some questions?
Yeah, the comment is that ABINIT is notoriously hard to install. And so I was wondering if Corvus worked as well with things like Quantum Espresso.
Yes, I mean, we have a couple different things that it works with. I can't remember if we have quantum espresso yet, but we will. And you know, we do have some other things. We have an NWCHEM handler. Not that that quite takes the place, but anyway, that's something we plan on having, and I think that's a good point. ABINIT itself is, we shouldn't limit it to ABINIT. It's not supposed to be limited to any particular code.
That's good. And the one thing you didn't mention is why Corvus?
You mean versus other workflow machinery?
No, I mean, why the name?
Oh, well, I think the idea was that crows or blackbirds are notoriously good at basically running their own workflows. Right? They can perform complex tasks and actually come up with complex tasks. So they're actually automatically generating the workflows as well. Oh.
Okay, so John has a question too about remote installations.
I think he just wanted
John?
me to.
Okay, so why don't you continue, and we might ask questions at the end.
Yeah, I have that question is going to be answered in the next slide or two. So
Okay.
that John had. He was just, so let me see where I am here. Okay, let me go back to. Okay, so anyway, you can see that we're currently developing a lot of new handlers. I think Quantum Espresso should be on here as well. And then, for example, and then we're also working on a graphical user interface, and we've had some collaboration with Matt Newville as well on that. And if you're interested, you can take a look at our paper in Journal of Synchrotron Radiation here. And then also, this is, you know, important for Matthew's. Well, actually, I can't remember who asked this. Actually, maybe it was Matthew. But anyway, about having to install things. We're going to keep a sort of a software bank at the Theory Institute for Materials and Energy Spectroscopies, which is, you know, which is hosted at Stanford, SLAC. And so this is where this software is going to live. Corvus, along with all of the external codes that you might need, at least those that are open source. Obviously, we can't just give people VASP, but and then there also, I think, will be some way to run this on the Times dedicated server externally, you know, from some kind of web interface, at least in some fashion. I don't know whether, you know, at least to start, it will be probably more of a just trying things out. But I don't know how that will go in terms of production runs later. Okay, so anyway, thank you, everybody. And I just wanted to thank our other people in our group, as well as who have worked on this, as well as collaborators, and especially Jerry Seidler for setting all of this up. Thank you, Jerry.
Okay, any more questions? I think I don't see any more questions showing up in the chat, so I'll ask at least one, maybe a hard one. Can you talk a little bit about how much work or what sort of work is needed to add a module? Do you have to, is this working on getting the input and the output translated into some common format or something? And how much
That's
work
right.
is that really?
I mean, obviously, I guess what I would say is it's for someone who knows the code really well, it's not a huge amount of work. meaning knows the external code. And you don't
Yeah.
really need to know that much about Python. I mean, you know, need to know some, but I think it's, yeah. So, I mean, again, I think it's probably pretty easy. If we can actually enlist people, that's the best. But, you know, if enlist people that really know the code really well. And it also depends on exactly what the input and output look like. Some input and output is a little bit easier to deal with than others. But I think we're kind of building tools as well to deal with, because a lot of input and output has similar structure as well. You know, it has some kind of beginning and ending characters or something like that includes a block of input.
Yeah,
like
so actually, I see two questions from William and from Young, and I'm just going to paraphrase them. Can you say anything about like availability of Corvus and maybe availability of training or workshops on? So when will this be, you know, routinely available? And
I think we're planning on, well, okay, so I think in the next couple months or so, or maybe the next 6 months, we will be releasing this along with a new version of FEFF, FEFF 10. And so I think those together, we will start having workshops after that. Actually, that was another question. I see I have my chat here as well, but I see that was a question about the Slack users meeting, for example. I think that's a good idea. We may also have one that's, you know, from dedicated times, your workshop, for example. It's just hosted by Times.
okay, and Matthew Marcus has a question, and I'm not going to try to paraphrase it. So go ahead, Matthew.
Yeah, all of these programs like Quantum Espresso have a lot of parameters that you have to set. You have to set things like pseudopotentials and convergence parameters and so forth. And I was wondering how that, how Corvus does that. For instance, do you have to still do convergence testing to make sure that you're getting the right answers? And for pseudopotentials, like the X spectra requires special pseudos for the core hole.
Yeah, so I mean, I think that in general, the idea will be that you will be able to do a reasonable calculation from the start. I mean, not necessarily that you wouldn't want to go and do a convergence test or change your pseudopotentials, but we should have a bank of pseudopotentials that are reasonable, right? And so some calculations you can pretty much do with those pseudopotentials and be fine. Others you might have to specify your own pseudopotential with, you know, make sure that you have some semi-core states, for example. And I think some things could, sorry, go ahead.
Yeah, would it do things like set the K grids and so forth in some irrational way?
Yeah, I think it can do that. I mean, in some cases it is doing that. So for the phonon spectra, for example, it runs ABINIT in a very simple way, and ABINIT actually does that for it. It chooses some Q grids, and then it, you know, you get
Quantum
the Q grid
Espresso for the SCF, you have to define your K grid.
Mm-hmm.
And there's some rough rules of thumb as to how it works, as to how to do that. Like the Quantum Espresso input generator has those. But still, what I understand about these codes is that they will cheerfully give you nonsense if you don't use them just right.
Right. So a lot of those things can be done with defaults, but also convergence tests will be embedded in the workflow, or can be. Right. So that's one of the things that's somewhat new, is this recursive flow where you can make a workflow that you know, loops over one calculation and has a bunch of and tests for convergence.
Yeah, because what would
Or-
really make it accessible to the rest of us, as it were, is to have something where all those details are essentially hidden, so that you don't have to think about them.
Yeah, I think probably what would happen is that it wouldn't, you know, a convergence test probably wouldn't happen if you ask for a structure. You would probably specify you wanted to do a convergence test if you want to, just so that it doesn't, you know, take a billion hours right from the get-go, for example. But
okay, so William Holden also had a question about the IMAT-Gen, the materials project. Do you want to discuss that? And then William, if you have a follow-up, just blurt out and jump in. So I guess what's the relation with the materials project on this?
this doesn't really have so much overlap with the materials project in the sense of collaboration between, but I think there can be, right? At least as yet, right? But there can be in the sense that we might want to use their database to extract properties that they've already calculated, things like that.
Right. Well, I guess if William's not going to ask this, maybe so if they have, if you have some intermediate templating system for that, you know, and I think you do, that sort of helps to express the same concepts for all these programs, then can they just be generating, you know, effectively Corvus input files for you? And would that help everybody? Or should they be using Corvus?
I think once we have things at that point where we're releasing, I think that makes a lot of sense. Yeah, because I mean, as long as as long as our template matches what they're wanting to do, I mean, you know, yeah, I think that actually works fine. Yes. And I think they'd be able to do more complicated things with that.
Yeah, thanks, Matt. That's what I was getting at. I've just noticed that they have pretty extensive input-output library for all these different codes. I haven't tested any of them, so I'm not sure how well they parse stuff in and out, but it just sounded like there was a fairly, someone spent some time on it, so might be able to use a little bit of what they've done, but it doesn't seem like they don't have this big picture of properties and workflow that you have, so it's more like a input-output kind of question.
Yeah, I think they're more focused on having a a set of defaults that works for pretty much all materials, which is part of what we'll do for sure.
Yeah, thanks.
So that makes sense to collaborate with them on that sense, and we have.
Okay, and I think Yang Ha also had a couple more questions. Why don't you just go ahead and ask them?
Well, just have a comment. There's always needs to be a balance between the easy to use for beginners and be able to adjust some parameters for advanced users. So I'm just suggesting some default or some easy to use GUI for beginners, and for advanced users, they can really dig into the input file and just tune the parameters they wish.
Yes. Yeah, no, I agree with that. And I think we've, as a development strategy, always kept sort of an expert user type of, well, expert user possibilities there. So for FEFF, for example, you can give it a very minimal input where it has general properties are the only thing pretty much that you'd specify. Or you can give it, you know, FEFF specific properties or FEFF specific options as well. And there's an option for every single FEFF input card. So you can fine tune it if you need to, or if you want to. Okay, so
Okay, yeah, and Fernando, I guess Fernando also had a comment, but maybe you've covered that. I guess you're reading these also. So Samantha, if you have a question, why don't you ask us?
Yeah, I may have missed this, but can the user choose a workflow? And if so, does Corvus only have specific workflows to choose from, or can the user customize it?
So that's a good question. The user can definitely customize it based on the properties that can be specified or can be calculated within Corvus, right? There are also going to be more complex workflows that aren't easily customizable, that are more like a canned workflow. And then for, more advanced users, they might even write their own handler for a code that they know well so that they can add that to the list of properties that can be calculated.
Josh, can I make a comment?
Sure.
Yeah, this is Fernando. Hi. So in principle, there are two ways in which workflows can be generated in Corvus. One of them is basically in the way that Josh showed during the talk, in which you specify a property and the workflow is generated on the fly automatically based on the property that you selected and what codes are available. You can modify a little bit which workflow is going to be executed by telling Corvus which codes you want certain properties to be calculated with, okay? There's another way of generating workflows is you can write a Python script in a very specific Corvus-like language that allows you to just write the sequence of instructions that you want. As long as the properties, intermediate properties that you want are there, you can write them in such a way that this is going to write a workflow, store it in a file, and the next time that you run it, you can invoke that workflow and use it for doing your calculations. So there is a primitive way of doing it. And we are working into making that kind of thing a little bit better documented and more available. But that kind of possibility is there if you want. Okay, that was the only thing I wanted to comment.
Right, that might be a good way for the materials project to be able to use this too.